I'm Anastasia from Yahoo Research. I'm really happy to be here. And I'm going to talk about our joint work with Eshcar, Hillel, and Edward Bortnikov about two new features we add to the HBase in order to accelerate that. Okay? So what is the plan for today? I'm going to start. Do you hear me well? It's okay? Good. So I'm going to start with the background and with the motivation. I'm going to explain why have we done what we have done. And what we've done is actually two new features. Michael Stack talked about that in the keynote at the beginning. Okay, we have done the in-memory compaction. It's in a nutshell, it's similar to moving from disk compaction to in-memory compaction. And we have done another possibility to reduce the metadata we use per cell. Okay? So first, the motivation was Sieve, which is Yahoo real-time content management. Okay? I think that this work was already far beyond this motivation, but generally we start from here. Okay? So Sieve is a processing pipeline. There are many other processing pipelines. But what we do here, we take data from World Wide Web. We just have a processing pipeline of Apache Storm bolts. Okay, and HBase serve as intermediate storage here. Okay, we have producer-consumer relationships between the two bolts. Okay, we store data on HBase table, and then we use it to process the next one. Okay, so what is interesting about this? Workload? Okay, so what do we have here? Is small working set. Okay, just put messages. We put messages. It's not exactly the FIFO queue, but on some queue, and then we use them. So the lifetime of the message is short. We have high churn. The messages are updated, and also we scan those messages to find the new ones. Okay, so usually such a workload is not worked so well on the HBase because you have frequent flashes and then frequent compactions, and I think you know well that it's usually not work so well. Okay, so and of course, what is our goal is to get the better performance like everybody wants, and how we are going to be there is to use less memory. That's what we want. We are talking about MemStore. All the features are in the MemStore. We are talking about single machine, okay? And we want to fit more in same RAM, okay? We just want to put more there, and then we are going to delay the flashes to the disk, okay? Then if we have less flashes, we have less compaction, we have less I/O. We have better performance, hopefully, okay? So again, here are the two ideas. The in-memory compaction exploits the redundancies in the workload. If we update the same key again and again, we have multiple versions of the same key. If we delete the keys, we have Tombstones again. And if we hold everything in memory and then we wait till the disk compaction to get rid of all that, we spend memory in RAM. Okay? So the game is about duplicate ratio. In this case, if you don't have duplicates, if you don't have deletions, then actually you gain nothing. But if you do, then you can gain a lot. Okay, the next thing is to reduce the overhead we have per cell. It appears that when you put a cell or key value in the MemStore, there is an overhead. Okay, you use more metadata to serve this data. Okay, so actually, if we almost eliminate this overhead, and then you, again, can put more. Okay? So, again, here the gain is proportional to the cell size. If you have really big cells, then this overhead may be negligible for you. But if you have small cells, then you almost twice enlarge the memory if you take into consideration the metadata. Okay? So, once again, we want to prolong in-memory lifetime. We want to delay flash to disk. And then if actually every computer science student can tell you that it's better to be in RAM than to be on the disk, right? But generally it's more than that. It's more than that because if we delay the flash to disk, you have less flashes, you have less files on disk. All the files are used to be in HDFS, okay? So have replications all over the cluster, and it's the compactions themselves take a lot of resources. It's network, it's CPU cycles, it's disk bandwidth, so you save much more than just having something on disk. Okay? So I'm going to now to the details about in-memory compaction. Okay? So just to refresh your memory, here how we write in HBase. Okay, we just, all writes arrive to some active segment. Okay, then of course we write to val, write a head log in order to be persistent. Once this active component, this active segment is full, we are going to flash. We want to flash to the disk. How do we flash to disk? First, we save snapshot, right? I'm not saying something new here. Okay, we have snapshot. It means we have some immutable segment. This is very important for us. This thing is immutable. It's read-only. Okay, it's meant to be flashed to disk. Okay, so the next thing is really to write it on disk. It can truncate val, and we are going to compact on disk once we have enough files, and hopefully we'll get rid of all the unneeded data. Okay, this is how write works in default MemStore. Okay, how the read works. Also, as you know, we can read from active, from snapshot, and from the disk. Usually, we do not read from the disk. We hope to fit into block cache. Okay, so this is another possibility for the read. But once the block cache is full, okay, you have no choice, so you read directly from the disk. Okay, and this can be slow. Okay, once you compact on disk, again, you can fit into cache, and then you can improve the performance of read. Okay, this again the default MemStore. And this is what do we suggest. This is the new compacting MemStore. Here, in time that you want to flash to the disk, actually before you flash to the disk, you have so-called in-memory flash. What does it mean? You take the segment which is currently active, you put it to be read-only. Okay, you put it aside in memory, and then you have new active segment, the empty active segment where you can absorb all the writes. So far, understandable? Okay. So you can flash in the memory once again and once again, and you keep all those segments in the so-called compaction pipeline. Okay? Then you are going to compact them already in memory. Okay? Everything stays currently in memory. And you get rid of all the obsolete versions, deletions, and so far. Okay? Now, if you still need, okay, it's limited after all, so you may still need to flash to the disk. And that's what they're going to do. You can move this inactive segment, read-only segment, to the snapshot, and then flash it to disk if you have no choice. Okay? So this is the new compacting MemStore. Okay. So somebody can tell me, can ask me the question, why do you need this? Because if you're going to flash it to the disk, okay, then you're going to compact it on the disk. Maybe everything fits to the block cache, and then you again serve from RAM, right? Like what for all these compactions? But pay attention that you said flash to the disk and compaction. And this is what we want to avoid, right? So we look on the compaction pipeline. If you compare the compaction pipeline to the block cache, like a write cache, we want to delay writing to the disk. And you can look on the block cache like read cache. And if you already read from the disk, then at least keep it in memory. Okay. Again, we have another trade-off here. When you compact in memory, you use CPU cycles. Okay. Of course, it doesn't come for free. So, but still, if you have less I/O after that, then it's worth it. Okay. So the trade-off between the two. So again, this all worth it if you have enough duplications. Okay, but we will see that we have the second feature that works for you even if you don't have replications. Okay, so let's see some evaluation of this feature only. Okay, so what is our settings? We use YCSB to compare between compacting MemStore and default MemStore. Okay, we have a small cluster of 3 machines, 1 region server, Heap space is 1 gigabyte. We use mslab, if you know those chunks, to write sequentially all the data. For default MemStore, we just, as I said, we have a trade-off between block cache and the compaction pipelines. So for default, we use 128 megabyte for flash. For when it's the limit when to flash. Okay, if you have 128 megabytes in the MemStore, then you flash to disk. Okay, for compacting, we a little bit enlarge this limit, and we decrease the size of the block cache. Okay, so once again, for default, for this experiment only, we put 128 megabyte, the limit to flash on the disk, and the 100 megabyte block cache. And for compacting, 192 megabyte flash cache and less block cache. Okay, this is just a trade-off. Okay, we do use duplications. Therefore, we have high-churn workload. We have 128,000 records, and each record is in the size of 1 kilobyte. We usually do 50% reads, 50% writes, and this is when we measure read and writes. And when we measure scans, we use 1% scanned and 90% writes. Okay, so let's continue to the graph. Okay, so what you see here, the blue thing is compacting, the red one is default. Here you see latency of read operations. Okay, the general workload is 50% read, 50% write. Okay, and here's the timeline, like the time progress to that direction. Okay, so generally the lower the better. Those things are flashes to disk, all the jumps in the default MemStore. The higher jumps are compaction on disk. Okay, and actually at the beginning, data fits into cache. This is also flash to disk, and if it still fits into cache, then you have approximately the same performance. Okay, but after all, you can see that we still continue to serve from RAM while this thing goes to disk and back to cache and all the stuff. Okay, this was Zipfian distribution. And here we have uniform distribution. It looks a little different, but again, you have all the flashes to the disk, and we still serve from RAM. Okay? And we can take a look on scans. Scans are more noisy, but still you can see that the blue scans can be seen underneath the red ones. Okay? Questions so far? Yeah.
The same data what you just wrote?
Can you repeat?
The reads which you are doing is the same data which you were updating?
Yeah, the same
data being
Zipfian distribution or uniform distribution.
Okay, thanks.
Okay. Yeah. Do you want mic?
Yeah, so several slides earlier, you mentioned the heap size is 1 GB.
Yeah.
That's not realistic, right? Have
you
done, at my employer, by default, the minimum heap is 2 GB.
Okay. We understand that it's like not a perfect workload. We just use it of course, we need much more research to do and to use it in different configurations and to see how it works. That's just the machines that we had, so we continue the same way as it was. Okay, we can decrease, we can try it in other ways, decrease the heap size, increase the heap size, and see how it goes. But generally, it's less dependent on the heap size. It's dependent on the size that you give yourself to flash to the disk. Okay, you have more heap, maybe you waste it. Okay, but still, the most important thing is 128 megabytes I'm going to disk. This is my limit in the MemStore. Okay? One more.
So what was the amount of duplicate data with these runs?
As I said in the beginning, we have 5 million operations, and we have 128,000 records. So just divide it.
Entries in there?
Excuse me, can you say again? Duplications? In the same, I don't hear it, I'm sorry. Oh, okay, I'll talk to you offline, okay? Okay, so we are done with the compacting MemStore. I'll answer more questions. Oh no, we are not done yet. We are not done, sorry. I'm going to show you how we do together with deletions. Okay, so just a brief, because it's already maybe not so interesting. When we have deletions, we do go to the disk, also on the compacting MemStore, but we have much less flashes and less disk compactions, and this is the important thing. Okay, so here you see again the red one is the default MemStore latency, and the blue one is the compacting one. But the important thing that we had only 2 flashes to disk and 1 disk compaction. Like this is the disk compaction that we had, and for default we have in total 15 flashes and 4 disk compactions. Okay. Those are the flashes, and the same about uniform distribution, and the same about scans. Okay, this may be less interesting. So now I'm going to talk about index reduction. Okay, let's switch to some other problem. Okay, we want to use less overhead per cell. Okay, it's not related already to the duplications. Okay. So this is what we have already seen. And let's take a close look on the segment, okay? As I have said, all those are segments for us. This one is mutable, and all those ones are immutable. Okay, and this is the important thing, as I have already said. Okay, so let's look on the immutable segment. What we have here in the default MemStore. Okay, so we have mslabs. Mslab holds all the bytes of all the cells. Like all the keys, value, all what you have there is written there sequentially, one after the other. And it's written in the mslab in the order that we get it from user. It's not ordered according to the key. Just you get it and you write. Okay, then on top of it you have concurrent snap. It's log-free, it's nice. And why do we need it? In order to get everything ordered. Okay, so from the skip list, you are going to the cell object, and then from the cell object, you know how to get to the correct place in the mslab. Okay, so here how it looks. Those keys are ordered. Okay, those are the cell objects that redirect to the correct place on the mslab, and all those spaghetti pointers help you to locate the order. Okay. And actually, this thing is pretty big. It gives 100 bytes overhead per cell. Okay, if you have small cells, it's important number. If you have really big cells, it's less important. Okay, but where the twist is that you don't need this dynamic order in case you are immutable, right? It's just already ordered. It's good. So what we are going to do, we are going to remove the skip list and to use kind of cell array, okay, because this is enough. Why it's enough? Because you can use binary search. It searches in the same log n operations as the skip list, okay, and you don't need all the data of the skip list. Okay, this is the catch. So, so actually, this is what we have in the new immutable segment. And actually this is the new design. We manage everything and it's good for the scans. And we have better utilization of CPU. We have better utilization of memory. We use less memory. We have less fragmentation. It's better for the GC. And it's ready for the off-heaping. If you plan to off-heap everything that was in the MemStore, then you probably need this. Because skip list is actually not something you can take off-heap. OK? So how it works now, putting it all together. So when you have something, you want to make the in-memory flash. Then first you ask, are there enough redundancies to compact? OK, because maybe you don't have redundancy, you don't need to spend CPU cycles on the compaction. OK, if you have no redundancies, then just flatten the index. Just at least remove all the unnecessary memory. OK, if you have something to compact, then good. Just you do both, compact and present in the more effective way, efficient way. OK? So, after all of that are going to enter to the compaction pipeline and going to be compacted from time to time, as I said previously. OK? And if you need to flash, then again the same. Go to the snapshot and flash to the disk. OK? And we are going to continue. This is the new compacted MemStore. Okay, I'm going to continue to the evaluation results. Okay, here is the most interesting one. Okay, we have here a skip list-based compaction. This is the violet one, and the blue one is we call it cell array-based compaction for now. Okay, you can see that it's not compared to default. It's only compared to the skip list-based to the compaction one. Okay, so what you can see here, it's for small cells. Each cell here is just 100 bytes. Okay, you have flash to disk, then flash to disk again, then you have once again, and we are just serving from memory all the time. Okay, then you have not the same, but the interesting picture about 1K cell. When I have cell of size 1 kilobyte, it's already not so small, but still you have some improvement because we are going to disk much later than the original one. You see the blue one behaves almost the same, but with some delay. Okay? Then we have results for the scans. This is the scan for the big cells. And still you can see that the blue scan is going down. It's like just below the purple one. Okay? Those are really new results. I think nobody here saw it before. And we're just working on that. It's just really work in progress. Okay, so to summarize, to see how it goes, the first Jira, it was this number. It's already committed. And the first one is only about compaction. Okay, just compaction without the effective memory representation. Okay, so if you are interested, you can use this name, in-memory compaction true, when you create a table. So it's going to be compacted, if you like. And the index reduction is another Jira. It's still work in progress. It's still not committed. And the off-heaping should come on top of all of that. Okay? To summarize, once again, we have two new features in HBase. We use less memory, generally speaking. Therefore, we delay flashes to disk. And therefore, we have less compactions on disk. And this leads to possibility to take all the data, all the structures in the MemStore to be taken off heap. And we are really proud about that. It shows good results in practice. We would like to thank our reviewers. And